Hello everyone, I welcome you all to the Nano Next Horizons YouTube channel. Myself, Dr. Babu Batula, Professor and Dean, School of Sciences and Humanities, SR University, Warangal. Okay, so this is our fourth lecture in the series of nanomaterials for energy storage applications. In previous three classes, we have discussed about nanoscience, nanotechnology, nanomaterials. And also we have seen the importance of nanoscale, and also we have seen the how can we make macro materials into nanomaterials. The process with which we can make nanomaterials also we have discussed. And also we have discussed about the nanomaterials applications or nanotechnology applications in various fields like medicine, electronics, material science, and in energy sector also. So in this lecture, we are going to discuss about classification of nanomaterials. That means based on the dimensionality, we are going to discuss about classification of nanomaterials, that is zero dimensional materials, one dimensional materials, two dimensional materials, and three dimensional materials. So in this class, we are going to discuss this topic, right? So let me explain briefly about introduction to nanomaterials. What are nanomaterials? In our previous classes, in our previous lectures, we have in-depth discussed about the nanomaterials, right? So how can we define a nanomaterial? If any one of the dimension is less than 100 nanometers, that means either length or breadth or height, any one of the three dimensions falls under 100 nanometer, then we can say that it is a nanomaterial, right? It is a nanomaterial. So what is 1 nanometer? 1 nanometer is equal to 10 to the power minus 9 meters, right? 10 to the power minus 9 meters, right? So you can see nanomaterials are materials with structural features below 100 nanometer in at least one dimension. It might be three dimensions, a length, breadth, height. Both may be less than 100 nanometers. It is also a nanomaterials. But to qualify as a nanomaterial, one dimension, one dimension must be within 100 nanometers. Okay, right. So they exhibit unique properties due to high surface area, quantum confinement, and surface energy effects. We have discussed very clearly that there are two main reasons for the nanomaterials, right? Two basic properties, two very important properties for all the effects of nanomaterials, that is surface to volume ratio, and second one is quantum confinement, right? One is sur- surface area to volume ratio, and the second one is quantum confinement effect, right? So if a nanomaterial has high surface area to volume ratio, then it provides higher surface energy to participate in any reaction, so that the end application, so that the efficiency will be increased, right? So for a better nanomaterials, for ideal applications, we need nanomaterials with high surface area to volume ratio and also quantum confinement effect. So how this quantum confinement effect? So because of this quantum confinement in nanomaterials, we can see quantized energy levels, and also as the size of the particle, size of nanomaterial decreased, the band gap will increase. So by modifying the size of particle, size of nanomaterial or size of nanoparticles, we can tune the band gap. Once we can tune the band gap, we can tune optical properties, we can tune electronic properties. So to tune optical and electronic properties to reach our desired electrical and optical applications, this quantum confinement plays a major role. Okay, so due to high surface area, quantum confinement and surface energy effects, these nanomaterials show unique properties when compared to large particle size molecules. Okay, large materials, you can say macro materials. Okay, right. So how can we classify these nanomaterials? How can we classify these nanomaterials? So based on dimensionality, we can classify these materials: zero dimensional materials, 1D, 2D, and 3D materials. Here you can see zero material, 0D, one dimensional, two dimensional, three dimensional. So in the coming slides, we will see in detail about the properties and applications of these different materials, and also we will see some of the some of my research. So I have prepared different kinds of nanomaterials, from zero dimension to three-dimensional materials. I have prepared zero-dimensional material, one-dimensional material, two-dimensional material, and three-dimensional material for different purposes. For different purposes, we have already seen that nanomaterials can be used for for different applications in different areas, right? For energy applications, and also for environmental applications, for electronic display applications. So there are different applications for nanomaterials we can see in many fields. So likewise, out of my 15 years research experience, I have prepared so many nanomaterials: metal oxide nanomaterials, metal sulfide nanomaterials, okay, and also different morphology, different dimensionality nanomaterials I have prepared and I have tested for different applications. So in coming slides, with the information of the properties and applications, we have seen some of my research publications and some of my research articles, so that we can see the practical applications where we can use these different kinds of different dimensionality nano materials. Okay, right. So basically, there are four types of nanomaterials. Classification is based on dimensionality: 0D, 1D, 2D, and 3D nanostructures. Okay, so four types of nanomaterials we can classify. These materials differ significantly in morphology, properties, and functionality. What does it mean? See, quantum confinement and also surface area will change for these types of nanomaterials. Okay, so 0D, 1D, 2D, and 3D. So based on the dimensionality, they have different shape, different size. Obviously, the surface area will change with respect to size, with respect to shape, with respect to dimensionality, right? So that's why, so every nanomaterial, that is zero dimensional, 1D, 2D, 3D, every type of material, every type of nanomaterial has its own pros and cons, right? So there are some advantages for, and also disadvantages. Okay, so that means every type of nanomaterial has its own advantages to use in a specific application, specific end application. For example, for batteries we need one type of nanomaterials. For solar energy applications we need one specific dimensionality nanomaterials, right? For biomedical applications, we need some other dimensionality nanomaterials, because the surface area, the quantum confinement changes with respect to shape, size, right? So based on the dimensionality it will change, further which finally affects the final application. So we need to understand the pros and cons or the properties of all these different types of nanomaterials, so that we can choose, we can select a proper nanomaterial for your application. So all the materials are not suitable for your end application. Based on your application, based on your requirement, based on your demand, based on the application demand, you need to select proper dimensionality nanomaterial which offers you your required surface area, right? So that's why you need to understand the properties of different kinds of nanomaterials, right? So that is what it means. These materials differ significantly in morphology, properties, and functionality. The surface to volume ratio is critical in defining chemical reactivity and surface phenomena. So in our previous classes, we have discussed about the importance of surface to volume ratio, right? So as the surface to volume ratio increases, the active centers, the active atoms comes into picture, comes to the surface to participate in reaction, so that we can observe more reactivity, right? More reactivity. We can see more surface energy, we can see more surface phenomena, right? So that's why surface to volume ratio is very, very important to understand. And our selected nanomaterial should provide higher surface energy, right? Then see here, applications span electronics, medicine, energy, catalysis, and environmental remediation. So from starting onwards, we are discussing about these fields, right? So nanomaterials finds applications in various sectors, in electronics, in medicine, in energy, in environmental applications, so many applications, in defense applications, in space applications. So wherever you find, you can see the nanotechnology applications, right? So where we are using nanomaterials, right? Nanomaterials. Understanding dimensional classification helps in designing targeted applications. So that's what I discussed earlier, right? So you need to understand all these dimensionality materials. So different dimensionality materials offer you different applications, right? So that's why based on your target application, based on your required efficiency, you need to select proper dimensionality nanomaterials, right? So if you see here, so zero dimensionality material, 1D, 2D, 3D. So these are nanoparticles, fullerenes, nanotubes, nanohorns, nanosheets, nanolayers, nano arrays, nanotubes, right? So these are all different kinds of nanomaterials. Here you can see, so this is a 3D material, right? So this is 2D. You can see just like a sheet. Here you can see 1D quantum wire. So nano wire. So wire means it's in the form of nano wire, nano rod, nano tube. So it is one dimensional. Then zero dimensional material means quantum dot. We will further explain in detail. We will see different all these morphologies with real world examples, right? So this is 0D, 1D, 2D, and this is 3D nanomaterial, right? 3D nanomaterial, right? Zero dimensional nanomaterials, right? The first category is zero dimensional nanomaterials. Zero dimensional nanomaterials. See these images. See how beautifully it is, nanoparticles, right? Nanoparticles. So what are the examples for zero dimensional nanomaterials? So that is nanoparticles, quantum dots. Okay, dot is a particle, right? Dot is itself it is a particle. So nanoparticles and quantum dots are examples for zero dimensional materials, right? Zero dimensional materials. Here you can see, so the first image, the top image is the SEM image, scanning electron microscope. So I have told you earlier that to see nanomaterials, so microscopes are not sufficient. Okay, microscopes are not sufficient. We need electron microscopes, right? We need electron electron microscopes. Okay, right. So this is the scanning electron image of nanoparticles. You can see here, see from here to here. So this is 500 nanometers. This from here to here, you can see the dot, here to here. So this is 500 nanometers. So that, so the diameter of this nanoparticles must be less than 100 nanometers, definitely, right? So these are nanoparticles. And here also you can see, this is TEM image, transmission electron microscope. This is scanning electron microscope image of nanoparticles. This is TEM, transmission electron microscope image of nanoparticles, right? So 0D nanomaterials have all dimensions at the nanoscale. Example, nanoparticles and quantum dot. See, zero-dimensional nanoparticle itself, it is a, we can say that it is a 3D material, but very small size, very small size. Because nano 0D means, it doesn't mean, it doesn't have any dimension. No, it is length, breadth, height, everything, but very small dimensions. Okay, right. So they exhibit pronounced quantum confinement leading to discrete energy levels, right? Discrete energy levels, we have seen, right? In nanomaterials, quantum confinement creates quantized energy levels, discrete energy levels, so that the band gap will decrease because of the small size, because of small size. The higher surface to volume ratio enhances surface activity, right? So because of the small dimension, small size, it provides higher surface to volume ratio, it provides higher surface to volume ratio, it provides higher surface to volume ratio, right? So what is the use, what is the use of it? Because it enhances the surface activity due to higher surface energy, right? Due to higher surface energy, right? 0D materials show strong optical and electronic tunability. Okay, zero dimensional materials show strong optical and electronic tunability. So because of this property, because of this strong optical and electronic properties, because of electrical conductivity. So so in our previous classes we have seen, right, quantum dot LEDs. So what is the latest trend in televisions? QLED, right? QLED, quantum LED, quantum dot LED, quantum dot. Quantum dot is a zero-dimensional material, right? Quantum dot is a zero-dimensional material. So it provides very good optical and electrical properties. So that's why. So it is used in trending applications, right? In today's applications, quantum LEDs, quantum dot LEDs, right? Their small size and surface energy make them suitable for catalysis and also drug delivery. Okay, so in photocatalysis, for hydro, for water splitting, for dye degradation, right? So pharmaceutical dye degradation, right? Textile dye degradation, and also in medical field, in drug delivery, in targeted drug delivery, we will use these quantum dots because of its small size and unique morphology. It is a dot, so it can easily flow, right? It can easily flow, right? So that's why, so 0D materials have very advantages, particularly in the field of catalysis and drug delivery. Examples include gold nanoparticles, carbon dots, and semiconductor quantum dots. So these are some of the examples. Okay, some of the examples for 0D nano materials, right? So I will show you some of the gold nanoparticles that I have prepared in laboratory. So and also I have prepared semiconductor quantum dots, that is SNO2 quantum dots, tin dioxide quantum dots I have prepared and used for different applications. I will show you all these results. Uh, very soon. They are widely used in imaging, sensing, and targeted drug delivery system. So some more applications. So we can use these nanoparticles, these quantum dots in imaging purpose, right? In imaging purpose and also in sensing. In many sensors, we can use a SNO2 quantum dots also, and also we can use these zero-dimensional materials in targeted drug delivery systems also. We will use this one. So this is about zero dimensional materials. Okay, so what is this image? Scanning electron microscope, SEM, scanning electron microscope image. This one, TEM. T means transmission, transmission electron microscope, transmission electron microscope image of nanoparticles, right? This is scanning electron microscope nanoparticles. Okay, right. So coming to the properties of zero dimensional materials, properties of zero dimensional materials. Here you can see this image. You can see quantum dots. These are all quantum dots. So we already seen, discussed, even a small change in size in nano level, then itself it shows a significant or distinct difference in properties. Okay, here if you see here, so this is 8 nanometer nanoparticle, 6 nanometer nanoparticle, 5 nanometer nanoparticles, 4 nanometer nanoparticle, 3 nanometer nanoparticles. Okay, see quantum dot itself, it is a nanoparticle or nanomaterial, we can say. Okay, so don't confuse the terminology. Okay, so these are all nanoparticles at 8 nanometer to 3 nanometer. But see the difference in optical properties. See the difference in optical properties. 8 nanometer nanoparticle or 8 nanometer quantum dot shows red color, red color, right? Then 6 nanometer nanoparticle shows orange color, right? 5 nanometer nanoparticle shows 580 nanometer wavelength, right? Yellow color. Then 4 nanometer green, 3 nanometer blue color. So that means even the change at nanometer level, 5 nanometer to 6 nanometer, then there is a significant change in its properties, because once the particle size change, obviously what will change? Quantum confinement will change, surface to volume ratio will change, so that surface energy will change, the participation in reaction will change, finally the output, whatever it is, application efficiency will change, right? Right. Okay, we will see some of the properties here. High surface energy leads to strong interactions with surrounding environments. Okay, high surface energy leads to strong interactions with surrounding environment. So because of this high surface energy, it can react with other immediate surrounding, right? So for example, if you disperse nanomaterial into water, so all these nanoparticles immediately react with the water molecules immediately. So water is the environment, right? So if you disperse any quantum dots or any nanomaterials, so it can immediately disperse, it can immediately react with the surrounding medium. Okay, so whatever it is, if it is a air medium or water medium or some other medium, it can immediately participate in reaction, it can immediately react with the surroundings because of high surface area, because of high surface area. They exhibit size depend. Their photoluminescence properties arise due to quantum size effects. Okay, photoluminescence. Okay, absorption, photoluminescence. So these are all optical properties. Okay, these are all optical properties. See, this is luminescence. Okay, luminescence exhibiting light. Okay, so the photoluminescence is very different for different nano for different size nanomaterials. Okay, they exhibit size dependent band gap tuning, vital for optoelectronic devices. So we have seen in our earlier lectures that, so once we change particle size, that means we can tune the band gap, right? We can tune the band gap. If we tune the band gap, what else we are tuning? We are tuning surface to volume ratio. We are tuning surface energy, right? So that obviously it affects the efficiency of the devices, right? So here it is optoelectronic device. So optoelectronic device efficiency can change by tuning the size, by tuning the band gap, by tuning the surface area, by tuning surface energy, right? So that is important. Agglomeration is a common challenge due to high surface reactivity. Agglomeration means, for example, all the particles close to each other, attached to each other, right? So there will be agglomeration, right? There will be some agglomeration. So that is a common challenge in nanomaterials because of the small size. And also we can do one thing, that is functionalization. Functionalization is used to stabilize and tailor surface properties. Functionalization means, here you can see nanoparticle core, right? So this is a nanoparticle. So we can functionalize this nanoparticle. That means we can attach some other molecules, different molecules, right? Here some antibody, some carbohydrate, fluorescent dye, polymer brush, right? Different, we can change the surface energy. We can change the surface energy. We can add some other molecules to participate in different reactions, right? We can functionalize, so that because of this functionalization, we can provide more stable nanomaterials, right? More stable nanomaterials. So there are a lot of advantages for functionalization. So we will discuss in our in our later lectures. Okay, so functionalization is very useful to stabilize nanomaterial and also to change, to tune the surface energy. Their small size enables cellular level biological interactions, right? So because of this functionalization, we can find many bio-related applications, many bio-related applications. And also these zero-dimensional nanomaterials, nanoparticles and quantum dots can find applications in magnetic area and electronics, and also in optical behaviors. These are all size tunable properties. If you change the size, you can change the magnetic properties. If you change the band gap, you can change the optical properties. You can, if you change the surface area, you can change the electrical properties. So all are interlinked and all can be tunable. Okay, all can be tunable. Okay. Right. So before going to one-dimensional nanomaterial, we will see some of the practical examples for zero-dimensional materials. We will see practical examples for zero-dimensional materials. I will show some of my research related to zero-dimensional materials. Okay. Yeah. I hope you the Chrome that is visible to you, right? Yeah. Here you can see, yeah, band gap tuning and XPS study of SNO2 quantum dots. So I have prepared SNO2 quantum dots in 2018. Okay, so I have prepared. This is a semiconductor quantum dots, or you can say that a wide SNO2 is a wide band gap semiconductor. It is a semiconductor. So tin dioxide is a semiconductor. So I have prepared SNO2 quantum dots, right? SNO2 quantum dots. So tell me, quantum dot is a what type of material, what type of nanomaterial? 0D or 1D or 2D or 3D? 0D, right? 0D. Quantum dots and nanoparticles, right? These are all zero-dimensional nanomaterials. So I have prepared this SNO2 quantum dots for what purpose? So before seeing this application, I will show you. Yeah, you can see these are the transmission electron microscope images. Okay, transmission electron microscope images. So these are SNO2 quantum dots. Here you can see. So this circle, so this is a dot. Do you know, guess what is the size? See here, this is 2 nanometer. So this much distance is 2 nanometer. So this diameter is definitely below 10 nanometer, right? So this is a quantum dot. Okay, quantum dot, SNO2 quantum dot. These lines are crystal planes. Okay, so the gap 0.33 nanometer, that is the interplanar spacing. Okay, so these are the quantum dots. Okay, so this is a quantum dot, so this is a quantum dot. Okay, so here you can see the band gaps. So we are discussing about band gap, right? So if you change the size, then obviously what will change? Surface area to volume ratio change. What else change? Band gap will change, right? Here you can see the band gap. See, this is the pure SNO2 quantum dot, pure SNO2 quantum dot, and also this one is annealing. So after preparation of SNO2 quantum dots, I have heated the same SNO2 quantum dots at 500 degrees centigrade for 2 hours, so that what will happen? So because of annealing, the particle size will change. Once particle size will change, what else will change? Band gap will change. See here, so this is the SNO2 quantum dots, SNO2 quantum dots band gap. How much it is? 3.49 electron volt. Then after heating, after annealing, so the band gap shifted to 2.41 electron volts, right? 2.41 electron volts. Here also you can see the absorption edge will change. See, the color also will change. And I have done annealing at different temperatures. At different temperatures, let it be. This is as it is, as prepared SNO2 quantum dots, and this is annealed at 200 degrees centigrade, annealed at 300 degrees centigrade, 400, 500, 550, 600, 700. So at different temperatures, I have annealed this SNO2 quantum dots. See the color change. Color change means change in optical properties. Color change means change in optical properties. Why the optical properties change? Because of change of band gap. Why band gap changed? Because of particle size. Because of change in particle size, right? Change in particle size. Here also we can see the particle size. The particle size changes from, see here. So as the temperature increased, see this SNO to 200, 300, this is the temperature, right? So as the temperature increases, so the particle size is also changing from 2.3 nanometer, 4.6, 4.1, 5.2, 6.95, 6.95, 6.95, right? So as the temperature is changing, particle size is also changing. Because of change in particle size, because of change in particle size, here you can see, here you can see the change in band gap. See the band gap 3.49 electron volts, 2.95, 2.65, 2.51, 2.41, 2.44, 2.45, 2.52. Why there is change in band gap? Because of annealing, the particle size is changing. Because of the particle size changing, then the obviously optical properties will change, right? Band gap will change. Okay, I will also show you gold nanoparticles. Okay, gold nanoparticles. So this is also SNO2 quantum dots. Here also SNO2 quantum dots. These are all quantum dots. See this, these are all quantum dot cloud. Quantum, see every dot, you can see the dot dot dot. So all these dots are quantum dots. So we have seen, right, one of the properties is agglomeration. These are all agglomerated. These are all agglomerated quantum dot clouds. Quantum dot cloud. So okay. So all quantum dots close to each other. Close to each other. So these are all quantum dots. Okay. SNO2 quantum dots. I will show you another example for zero dimensional material. I'll show you gold nanoparticles. So this is my Google Scholar link. You can see all my research here, all the papers that I have published. You can see here. I will show you gold nanoparticles, right? Gold nanoparticles. Where is it? Yeah. See, it is a nano composite. So it is the combination of quantum dots and nanoparticles, right? So this is gold nanoparticles. It is slightly bigger in size when compared to this SNO2 quantum dots. Quantum dot is very very small, around 5 nanometer plus or minus. Okay, 5 nanometer. This is gold nanoparticle. Okay, you can see this is gold nanoparticle, gold nanoparticle, gold nanoparticle. This one, this one, this one. This dark dot, bigger dot, you can say. So this is gold nanoparticles. Okay, gold nanoparticles. But the shape and size is not uniform, but shape is almost close to spherical. So you can see this is a gold nanoparticle. So remaining things are all quantum dots. Remaining things are all quantum dots. You can see the very high resolution gold nanoparticle. So this is a gold nanoparticle, and this is it is surrounded by quantum dots. It is surrounded by quantum dots. Here also you can see clearly. So these are all quantum dots, and these bright dots, white colored bright dots. These are all nanoparticles. Okay, nanoparticles. So this is the HR10 mapping. It is called HR10 mapping. So see this one, gold. The red colored is shows the presence of tin, presence of SN. So this green color shows the presence of oxygen. Okay, and these yellow dots shows confirms the presence of gold nanoparticles. Okay, so these are all gold nanoparticles. So now you understood zero dimensional materials, right? Zero dimensional materials. The best examples are nanoparticles and quantum dots. I have shown you SNO2 quantum dots, tin dioxide quantum dots, and also I have shown you gold nanoparticles. Gold nanoparticles. So, so for what purpose I have prepared? I will show you the application. So the application is tuning. I have prepared this material for the textile dye degradation. Okay, so for rhodamine B, methylene blue. So these are the standard water pollutants. So to degrade, to reduce the water pollution, I have prepared this material. I will show you in some other application. Yeah, here you can see I have prepared gold SNO2 quantum dots composite for the what is the purpose? For photocatalytic application. Okay, for photocatalytic application. So like this. So this is the gold nanoparticle, and this is surrounded by quantum dots. Okay, quantum dots. By using visible light, So we have degrade this die. Okay, we have degrade this die. So for photocatalytic applications, for environmental applications, I have prepared this material and I have tested, and it performs well, and it is published in a very good journal, that is Ceramics International. Okay, right. So this is about zero dimensional materials. Now let's go back to our presentation. That is, let's go back to our presentation. Yes. So this is about zero dimensional materials, right? So just like our gold nanoparticles, so these are all nanoparticles. This is TEM image of nanoparticles. This is SEM image of nanoparticles. Now we will see one dimensional nanomaterial. Okay, one dimensional nanomaterials. So the next type of nanomaterial is one-dimensional nanomaterial, right? So previously we have discussed about zero-dimensional nanomaterial. Now we will discuss about one-dimensional nanomaterial. So what are the examples for one-dimensional nanomaterials? See here, these are all SEM images, scanning electron microscope images of nanotubes, nanowires, nanofibers, nanoribbons. Okay, so these are all the examples for one-dimensional nanomaterials. Okay, nanorods, nanowires, okay, nanoribbons, okay, nanostrips. So these are all examples for one-dimensional nanomaterials. We will see the examples, and also we will see the applications of properties of one-dimensional nanomaterials, and also we will find the applications of one-dimensional nanomaterials. Okay, sorry. Uh, one-dimensional nanomaterials have one dimension outside the nanoscale, like nanowires, nanorods, and nanotubes. What does it mean? For example, if you take any lengthy object like this, if it is a pen. So when compared to diameter of this pen, length is very long, length is very large, right? Length is very much greater than diameter of this pen, right? So likewise, so out of the three dimension, one dimension is out of the nanoscale. One dimension is out of the nanoscale means it is more than 100 nanometer, more than. So remaining things must be within 100 nanometer, but one dimension is outside because it is very long, right? That's why it is a one dimensional material. Okay, that's why it is a one dimensional material. So, right, so in this pen, diameter is very much less than length. Okay, right. So that's what the meaning of this one dimensional nanomaterials have one dimension outside the nano outside the nanoscale, like nanowires, nanorods, and nanotubes. Okay, right. So second point, yeah, the examples are nanowires, nanorods, and nanotubes. They enable unidirectional electron or phonon transport. So because of the higher length, because of high aspect ratio, that means length divided by diameter, like. So because of this high aspect ratio, and because of the one dimension outside the nanoscale, that means very lengthy one dimension. So it can offer unidirectional electron transport. Unidirectional electron transport. That's why it can offer higher electrical conductivity. Okay, higher electrical conductivity also. Okay, so their high aspect ratio supports unique mechanical and electrical properties. High aspect ratio means length divided by width or diameter. Okay, so that is high aspect ratio. For example, if it is higher length, then it offers high aspect ratio. High aspect ratio. Okay, then Applications include Applications include FET, field effect transistors, biosensors, and supercapacitors. So these one-dimensional materials can find applications in these fields. So there are some other fields also, but majorly this one. The surface to volume ratio is still high, aiding in efficient surface reactions. So at the end of this lecture, I will compare surface to volume ratio of different nanomaterials 0D, 1D, 2D, and 3D. Okay, we will compare later. Okay, still the surface to volume ratio for 1D nanomaterials is good, it's high. So examples are carbon nanotubes and TiO2 nanorods are common examples. Okay, so their anisotropic nature is exploited in energy devices and sensors. Okay, so these one-dimensional materials can be used in energy storage devices like supercapacitors and battery, and also energy related applications like fuel cells. Okay, and in sensor applications also. Okay, so this is about one dimensional nano materials. See, you can see here. So if you compare with diameter, for example, if you see, um, I will increase this. So here you can see, this is the wire, right? This is the wire. So you can see, when compared to diameter, the length is very high. So that's why, sorry. So that's why in the first sentence here you can see 1D nanomaterials have one dimension outside the nanoscale. This is the length here. Length is, in this case, length is outside the nanoscale. Length is very long. It is far more than 100 nanometer, right? This one. So these are all, length is very high. Yeah. So this one dimension, these nano wires or nanotubes are examples for one-dimensional nanomaterials. Okay. So let's go back. Then, yeah. Then coming to properties of one-dimensional nanomaterials. Properties of one-dimensional nanomaterials. So these are the nanorods, CDS nanorods, and also you can see agglomerated something particles like, so that is quantum dots. So I have prepared this CDS nanorods along with SNO2 quantum dots for photocatalytic application. Okay, for photocatalytic application. You can see the, yeah. First we will discuss about the properties. Okay, properties. Then we will discuss about this image. Okay, so electron and phonon transport is highly directional due to one-dimensional structure. Okay, so we already seen that because of the unidirectional property, so one-dimensional nanomaterials offers higher electrical conductivity, right? Higher electrical conductivity. So surface states influence conductivity and reactivity in devices. So because of this unidirectional nature, so it offers higher electrical conductivity. So this, because of this property, we can use it in many electrical applications also. Okay, so the surface states influence conductivity and reactivity in devices. Carbon nanotubes exhibit exceptional mechanical strength and thermal conductivity. So, carbon nanotubes are very famous and familiar for one-dimensional nanomaterials. So, in CNTs, we have single-wall CNT, multi-wall CNT, right? Double walled CNT. So different. So and also different diameters, different diameter carbon nanotubes are also available for different applications, for different efficiencies, right? So this one-dimensional nanomaterial carbon nanotubes offer exceptional mechanical strength and thermal conductivity also. So quantum confinement in radial direction affects band structure. Okay, so these one-dimensional nanostructures offer fine tuning of band gap also, fine tuning of band gap also. So and also surface defects and dopants modify electronic properties. So similar to see in any kind of nanomaterials, be it zero dimensional, 1D, 2D, 3D, we can tune the properties. We can do doping, we can functionalize, we can make a composite, right? So there are many ways to tune the properties. There are many ways to tune the properties. Okay, surface defects and dopants can modify optical and electrical properties. And also because of this nano wires, nano rods, so they are flexible, right? So if you wire is somewhat flexible, right? Flexible. If you take any wire, for example, if you take, yeah, you can take any wire, you can take any wire, it provides some flexibility, it provides some flexibility. So because of this flexibility, so we can use in wearable electronics. For example, nowadays we are using smart devices, right? Flexible electronics. So you can put a smart watch, right? Smart watch. So it's curve, and also nowadays we are using foldable phones, right? Foldable phones. So how it is possible? So because of the flexible electronics, because of the flexible electrons, even though if you bend, so the electrical nature still exists. So that's why high flexibility and tensile strength benefit mechanical and wearable electronics. And also functionalized 1D structures improve sensor sensitivity. Because of the functionalization, we have seen the right. What is functionalization? We have seen in 0D nanomaterials. So we can functionalize the surface. We can attach some other molecules, some polymers, so that we can functionalize the surface to improve, right? To improve the final output. Okay, so functionalized one-dimensional structures improve sensor sensitivity, right? So these are the some of the properties of one-dimensional nano materials. Now we will see yeah. So these are CDS nano rods, cadmium sulfide nano rods. Okay, cadmium sulfide nano rods. So we will zoom it. Okay, yeah. Mm. See here, this is the images, top two images. So these two are scanning electron microscope images of CDS nano rods. Okay, I'm repeating, the two images A and B are the cadmium sulfide nanorods. Some images, scanning electron microscope images. Okay, so this is a single material. This is a single material, CDS nanorods. See the structure, how uniform it is, and also you can see that the length of rod compared to diameter. It has high aspect ratio, right? These are all nanorods. You can see what all are nanorods. Okay, this is the example for one-dimensional nano material. One-dimensional nano material. So I have prepared these CDS nanorods, and also I have decorated these CDS nanorods with quantum dots. Okay, with quantum dots. So this is a nanorod. Okay, this is a nanorod. So over the nanorod, so I have decorated with quantum dots. Okay, quantum dots are very small, right? Ultra small. So ultra small nanoparticles is quantum dots. So I have decorated SNO to quantum dots over the CDS nanorod. Over the CDS nanorod. That's what it is. Okay. You see this image D. See here, the surface is smooth. The surface is smooth because of the single material. So here I have quoted SNO2 quantum dots over the CDS nanorods. That's why you can what is this structure? Core shell. CDS nanorod is the core. Core. Nanorod is the core. Then we have decorated quantum dots. Quantum dots forms a shell. Forms a shell. Okay, it forms a shell-like structure. That's why we can call it as a core shell nanorod. Core shell nanorod. Okay. So that's why you can see here, this is core shell nanorod. So I'm increasing the quantity of quantum dots so that the shell thickness increasing, right? And the shell thickness can be increased. You can observe here. See, more thickness. If you see the thickness of the rod is small, then here increased, and again further increased, and again further increased. So after certain limit, so all these quantum dots formed separately. The additional quantum dots forms agglomerated quantum dots. Okay, agglomerated quantum. Here also you can see. See, already here the nanorods are covered with quantum dots, already formed core shell. The excess quantum dots, the excess quantum dots formed like a separate entity. Okay, so this is core shell nanorod. CDS nanorod is the core, SNO2 quantum dots as a shell. Okay, let's go back to original article. So where for what purpose we have prepared this material, and also how we have prepared this, I will show you. Now I will take you to the website. Just wait a second. Right. Now I will show you this CDS nanorods. Yes. See, this is the process I have adopted. So I have prepared SNO2 quantum dots. First, I have prepared CDS quantum dots, sorry, CDS nanorods, and then I have separately prepared colloidal SNO2 quantum dots, and then so I have added this SNO2 quantum dots, and by using sonochemical approach with ultrasound, so I have prepared core shell nanorods, right? So these are the CDS nanorods. I have added SNO2 quantum dots. So then I have prepared CDS nanorods decorated with SNO2 quantum dots, core shell nanostructures. Okay, so this is the XRD. So just I will show you the, yeah, I will show you this image. See this one. So this is pure CDS nanorods. These are the nanorods, nanorods, nanorods. See the surface very smooth. The surface is very smooth. Okay. Then here you can see the nanorods decorated with quantum dots. Okay, the nanorods decorated with quantum dots. You can see all this agglomeration, all this rough surface. This rough surface is due to the attached SNO2 quantum dots. That is as a shell. So here the core is nanorod, the shell is SNO2 quantum dot. Okay, SNO2 quantum dot. Here also you can see this is this lengthy one. This is nanorod, and these are all quantum dots decoration. Okay, so attached. So as we increase the quantity quantity of these quantum dots, so the thickness of the combination, the thickness of the combination as an CDS nanorod and CDS nanorod, CDS nanorod, and then shell. Okay, forms the shell. Okay, core shell nanostructure. Okay, so this is the core shell nanostructure. Core shell nanorods. Core shell nanorods. CDS nanorod as a core, shell is SNO2 quantum dots. Okay, yeah, you can see here also you can see this. This is, yeah, this is sulfur CDS. This is CD conformation, and this is SN conformation, and this is oxygen conformation. Okay, so this is HR10 mapping. So HR10 mapping used to confirm the elements of the material. Okay, so CDS, CDS, SNO2, SNO, oxygen. Okay, so this is the CDS SNO2 core shell nanorod structure. Okay, right. So these are the examples, and also I will show you some other core shell nanorods. I will show, yes, here. See here also you can see core shell nanorods. I have prepared and published in 2023. So I have prepared zinc tungsten, nanorods. Okay, I will show you the images here. So yes, this is for supercapacitor application. So previously CDS SNO2 nanorods. So this I have utilized for uh, yes, yes, for dye degradation application. For photocatalytic application, I have prepared this combination, and this one, yeah, this core shell nanorods I have prepared for supercapacitor for energy storage application. Okay, you can see here. So this is the charging and discharging. So this is the application. Okay, so one-dimensional nanomaterials we can use in many applications for environmental applications and also for energy applications. I have shown you my research. So I have prepared CDS nanorods. Let's go back to presentation. Let's go back to presentation. It is okay. Right. Right. So I have prepared this material for photocatalytic application, and also I have prepared other combination zinc tungstate SNO2 quantum dots for energy related applications, for energy storage device like supercapacitor. Okay, this is about one dimensional material. So far we have discussed two types of nanomaterials. Okay, one is zero dimensional material, and second one is one dimensional material. Okay, then we'll go further with two-dimensional nano material. Okay, two-dimensional nano materials. Okay, 2D nanomaterials, right? Yes, here you can see two-dimensional nanomaterial. Two-dimensional nanomaterial means you can imagine a sheet, a paper, right? You can imagine a paper. So this is a two-dimensional material. Okay, you can 2D sheet. Okay, you can. This is the example. So this is a two-dimensional material. Okay, two-dimensional sheet. Okay, two-dimensional two-dimensional sheet. This is a 2D material, right? And you can use this also, you can 2D shape, right? This is a 2D shape. Okay, right, likewise, but not that much thick. You can imagine as a nano size. Okay, nano size. Okay, so here you can see some flower like structures. So these are all flakes, nano flakes, nano sheets, nano pebbles. Okay, you can call it like that. Okay, you can call them like. So these are all examples for 2D materials. You can make 2D materials of different group of materials. You can graphene. Graphene is a famous two-dimensional material. Okay, and also amaxins at present, so trending two-dimensional materials. Okay, MOFs, metal oxide, metal organic frameworks. Okay, oxides. So there are so many materials can be prepared in 2D form. Okay, in 2D form. Okay, so right, we will see what are the advantages, what are the pros of this two-dimensional material, what are the properties, and where do we find the applications for two-dimensional materials. Okay, two-dimensional materials. So let's see point by point. So 2D nanomaterials have two dimensions in the nanoscale and extend laterally in one dimension. So for example, in zero-dimensional material, all the dimensions must be within nanoscale, within 100 nanometer. Okay, but in case of one dimensional nanomaterial, one dimension must be beyond nanoscale. Okay, beyond 100 nanometers, above 100 nanometers. But in 2D, in 2D materials, see, two dimensions two dimensions in the nanoscale and extend laterally in one dimension. For example, if you consider this paper, if you consider this paper, the thickness, if you just imagine this sheet as a nano sheet. Okay, nano sheet. This thickness, must be within nano. Okay, within nano, within 100 nanometer. But the length and breadth, length and you can length and breadth, this dimension. So out of this dimension, so this dimension and this dimension, for example, if you take paper like this, so this one beyond nanoscale and this dimension beyond nanoscale. Okay, so only one dimension within nano and the remaining two dimensions beyond nano. Okay, so for example, if you see here in this image, you can see this thickness, this small, you can see the thickness. I use, yeah, I hope yours, my cursor is visible, right? So this thickness must be within 100 nanometer, within 100 nanometer. Then if you check this length, it is, it might be beyond 100 nanometer, right? Beyond nanoscale. So that means this thickness must be within 100 nanometers. Then only we can say that it is a nano sheet. Okay, nano sheet. So here also the thickness must be within nanoscale and other two dimensions, it can beyond nano scale. Okay, so that is the meaning of this sentence. Okay, 2D nanomaterials have two dimensions in the nanoscale and extend laterally in one dimension. Okay, right, they possess large surface area with atomic level thickness, enabling unique surface phenomena. So if you when compared to one-dimensional material, two-dimensional material can provide high surface area. For example, if you take a sheet, for example, if you yeah you can if you roll this like this, okay. So if you roll this one, so this is let it be nano tube, okay, nanotube. So this nanotube, the surface area is very small, the surface area is small, but if you stretch this one, you can find you can find more surface area, you can find more surface area. That's why 2D materials 2D materials can provide better surface area, just like graphene sheet, amexin sheets, like that. So yeah, they possess large surface areas with atomic level thickness, enabling unique surface phenomena. Unique surface phenomena. Examples: graphene, amexins, transition metal dichalcogenides (TMDs) are common 2D materials. These are common two-dimensional materials. So I have prepared amexins and also some other. I have prepared graphene sheets, graphene also using modified Hammers method, and I have prepared graphitic carbon nitride. It is a good 2D material for photocatalytic applications. I will show you my research related to two-dimensional nanomaterials. Okay, right. So quantum confinement occurs in one dimension, altering optical and electronic properties. So as we discussed earlier, quantum confinement plays a big role in deciding the band gap, right, in band gap. So because of this modified band gap, we can tune the optical properties and electronic properties for different applications. Their surface area is fully exposed, making them highly sensitive to external stimuli. So, because of the high surface area, because of the layered structure, so most of the atoms comes into the picture, comes onto the surface, so that we can have more active centers, active atoms to participate in a reaction. So that's why it is very sensitive to react immediately, because most of the atoms at the surface level. So that's why the surface can be fully exposed, right, fully exposed. So where do we find applications? Applications include flexible electronics, supercapacitors, gas sensors, many areas. So as we discussed earlier, for example, if you want to make a rollable rollable displays, flexible rollable displays, you need such kind of nanomaterials, two-dimensional materials, right? Flexible, for example, yes, you can, the paper is very flexible, the paper is flexible, right? And also it provides good surface area. So two-dimensional materials can find applications in, across many areas like flexible electronics, supercapacitors, and also gas sensors. And also not only optical and electrical properties, it provides better mechanical properties. It provides very good strength, right? So that's why. So we can make this. We can use graphene, these 2D materials for high strength materials. Wherever we require high strength with light weight, we can use these graphene sheets. See here, their high mechanical strength and conductivity support integration in nanoelectronics. Okay. So we will show some of other properties. Yes, properties of 2D materials. So one of the, as we discussed earlier, just now. So high surface to volume ratio enables superior adsorption and catalytic behavior. Okay, superior adsorption and catalytic behavior. Quantum confinement along the thickness provides tunable band gaps. Okay, in tunable. So this is, yes, see this layered structure. So this is graphitic carbon nitride, Gc3N4, graphitic carbon nitride. So here I have tuned the band gap. So by using cobalt doping, okay, cobalt doping, we already discussed, right? We can modify optical properties and electronic properties by modifying modifying this energy levels, right? So by tuning, by doping with doping or by tuning the surface, that is functionalization, or by making composite, we can tune optical and electrical properties. Okay, their large planar surface allows easy functionalization and hybridization. Okay, so and also exceptional in plane conductivity and mechanical flexibility are key benefits. This is very important point regarding two-dimensional materials. It provides better mechanical flexibility. Okay, and also they exhibit strong anisotropy in transport and optical properties. Okay, so for electrical conductivity, so electrical pathways, so this 2D materials, particularly graphene, have very good advantages. So single or few atom thickness leads to ultra low weight material. So because of the layered structure, multi-layered structures, so they provide few atom thickness. So that, for example, if you take a nanoparticle or nano rod, nanotube, the thickness is higher. The thickness is higher. But if you make a layered structure, so that two layer, three layer, four layer, five layer structure, so graphene layers, so it can provide very low thickness, right? Very low thickness. So because it has more advantages wherever we require low thickness material. Okay, low thickness materials. Okay, wherever we need required low thickness materials, so these materials can provide better uh, advantages. Okay, and also, so they are ideal for high speed transistors and photo detectors and wearable sensors. Okay, so we can find many applications in many areas. Okay, many applications in many areas. Okay, right. So these are the properties of 2D materials. So we will see the practical examples. So I have prepared this uh, GC3 and 4. I will show you the real examples. Okay, I will show you my research papers uh, of this 2D nanomaterials. Let's go to this. Let's go to 2D materials. I think I haven't seen you one-dimensional material. This one, yeah. This is copper nanowires, one-dimensional materials. Uh, you can see here different. Yes. So these are all copper nanowires. Copper nanowires. So we have modified aspect ratio. So these are all copper nanowire solutions with different conditions. So we have seen earlier, right? So I told you how can we modify. So in synthesis process, we can modify in many ways. Okay, we can modify in many ways. So by changing the reaction time, by changing the temperature, hmm, by changing the pressure, temperature, duration, time, precursor conditions. So these are the examples for one-dimensional nanomaterials. So now we are in two-dimensional nanomaterials. Yes. See the layered structure, MOS2 nanopetals, MOS2 nanopetals. But I want to show you GC3 and 4. Yeah, this is a 2D material. This is a hexagon. Uh, this is zinc aluminate, I believe. Yes, zinc aluminate. So it's a 2D sheet with hexagon shape. So it is a two-dimensional material. Okay, I want to show you. Yes, see this one. It's a 2D material, two-dimensional materials. But if you see under scanning electron microscope, it looks like this. Okay, it looks like this. So these are all different conditions. So the first one is original as prepared graphic carbon nitride, and under these images cobalt doped graphic carbon nitride. Okay, cobalt doped graphic carbon nitride. Uh, okay, so here you can see the layer structure. So TEM is has more advantage because of its principle. It is a transmission electron microscope. Okay, transmission electron microscope. Here you can see the layers, right? The layered structure. So layered means it may not be exactly like a paper, exactly like a paper. It's a layered structure, right? It's a layered structure. You can see the two-dimensional graphic carbon nitride. So for what purpose we have prepared? So this one, yeah, for yes, for PEC application, for water splitting. So water can be split into hydrogen and oxygen, right? So for water splitting application, we have prepared this material. Okay. Yes, here you can see the change in band gap, tuning in band gap. You can see. So this is original graphite carbonate. This is 5% cobalt dope, 15, and I think some weight ratio. So different cobalt content combination. So here the band gap is changed. You can see here the change in band gap. See the from it was tuned from 2.71 electron volts to 2.62 electron volts. This band gap change can influence the efficiency. Okay, the efficiency. Here you can see the application. So it provides more current. Yes. See the application increased, enhanced, right? So this is one of the examples for two-dimensional materials in energy applications. Okay, in energy application. So is there any other 2D material that I have prepared? Yes. Here also you can see the nanoflakes two-dimensional structure. Here see you can see the image. It's a 2D structure, nanoflakes. Okay, the thickness is small, but you can see this side and this side it is beyond nanoscale. Okay, so this is the it is a composite actually. It is a composite. Okay, so these are one-dimensional material. This is 1D and 2D combination. 1D and 2D combination. Okay. So that's why you can see here. It's a 1D 2D combination. Okay. So this one also used for water splitting application. Okay. Water splitting applications. Okay. Then let's go back to our presentation. Sorry. So these are the properties of two-dimensional nanomaterials. So far we have discussed zero-dimensional materials, nanoparticles, nanoparticles and quantum dots, and then one-dimensional materials, examples, nanowires, nanorods, nanotubes, right? So these are all examples for nanorod, 1D nanomaterials. Then 2D materials, okay, 2D materials. Best example, graphene, amexin. So you want to see what amexin? I will show you amexin. Amexin. I will show you. See, these are amexin images. Okay, so these are all amexins. You can see the 2D structures, 2D layers, layered structure of amexins, layered structure of amexins. You can see all these images. So these are all very good. At present, most of the researchers are working on two-dimensional materials. Okay, on two-dimensional materials, particularly amexin for energy storage applications and also mechanical, electrical, whatnot. In many applications, at present we are using. So, a decade ago, graphene is very trending material. Nowadays, amexins are very trending and find many applications in many sectors, many areas. Okay, so these are all, you can see the beautiful amexin layers. You can see the beautiful amexin layers. Wow, right? So these are all examples for 2D materials, two dimensional. So these are all SEM images, SEM images, scanning electron microscope images of two-dimensional nanomaterial. That is amexin. Okay. So then we will go back to our presentation. Right. Now the fourth category, the last category in the classification of nanomaterials is 3D nanomaterials. Okay, 3D nanomaterials. I hope you can see the images, the beautiful nanostructures, right? Looks very beautiful. Three-dimensional nanostructures. The sphere, right? See this flower type. See, we have seen in earlier lecture that biomimicry of nanomaterials. Okay, biomimicry of nanomaterials. I will show you what is biomimicry of nanomaterials. Biomimicry of nanomaterials. It looks very interesting. See this one. So naturally, it has nanoporous structure. Naturally, it has nanoporous structure. Because of this thing, it can easily climb any vertical walls, right? So this is, and then you can see, so nanotechnology inspired from nature. We will show lotus example, right? Yeah, this one. So this is a lotus leaf. So on the lotus leaf, we can see the surface like this, surface like this. So these are all nano because it provides hydrophobicity, hydrophobicity, right? Hydrophobic layer, right? So these are all three-dimensional nanostructures. Three-dimensional nanostructures. Okay, we will see some important points. 3D nanomaterials consist of nanoscale building blocks forming a bulk structure. What does it mean? If you take 0D, 3D, 1D, 2D, so but 3D is very significant difference. It looks like a bulk shape. It looks like a bulk shape. Okay, but it must be within 100 nanometer. So all the dimensions should be within this 100 nanometers range. So that's why 3D nanomaterials consist of nanoscale building blocks forming a bulk structure. Okay, examples including nanocubes, nanoflowers, nanoporous frameworks, and aerogels. So these are all examples. We can call it as hierarchical structures. Okay, hierarchical structures. So they integrate nanoscale properties with macroscopic stability and processability. Yeah, so in macroscopic stability, usually macroscopic materials are stable, right, or stable. So these 3D structures can bring that nature at nano level, at nanoscale. So that's what it means. And also, the unlike 0D and 1D, 3D nano structures can provide high porosity. High porosity. You can see all the gaps within the material, all the gaps, all the voids within the material. So that is the beauty of three-dimensional nanomaterials. Okay, three-dimensional nanomaterials. High porosity and interconnected networks enhance mass and charge transport. Okay, so 3D materials provide high porosity, high porosity and interconnected networks enhance mass and charge transport. Surface and internal nanostructures offer multifunctionality in devices. So, because of this high porosity and bulk-like structure, so and also because of more stability uh, and processability, we can repeat uh, easily when compared to 1D and 2D. We can repeat the morphology into even large scale also. Okay, so that's why it provides multifunctionality in devices. Okay, 3D structures are used in catalysis, tissue scaffolds, and battery electrodes. So this is very important. In energy storage devices, particularly in supercapacitors and lithium-ion batteries or any battery, sodium-ion battery, lithium-sulfur batteries, 3D structures plays excellent role. It can store more energy. It can provide high energy density and high power density. Okay, so that's why 3D materials, the preparation and study of the 3D nanostructures in energy storage field is very promising. Okay, their design flexibility enables hierarchical architectures for energy applications. That's what I told you, right? So for 3D preparation of 3D, different structures can be prepared, and it can provide various diversion, diverse applications, diverse nanostructures, diverse shapes. So that's why we can say it is we can prepare multi advantages with this 3D structures. Okay, So coming to the properties of 3D nanomaterials, they exhibit combined advantages of nanoscale reactivity and bulk structural integrity. So we have discussed this point. So because of the bulk structure, bulk structure, it brings many advantages which we cannot find in 0D, 1D and 2D. So that's what the advantage of this three-dimensional nanomaterial. They offer high surface area and porosity, enhanced catalytic and energy storage applications. Right. So because of high surface area, so it provides porosity. Right. Because of this porous structure and this bulk structure, bulk structure within bulk structure, we can find porosity. We can find porosity. We can find different shape, right? Different shapes. Here, if you see here, you can see these are these are all looks like nano needles, right? Needles. So within the needles, we can find porous structure, and also this one also this one kind of flower structure. So within this structure, we can find porous structure. Okay, porosity. So because of sorry, because of this porous structure, so it can store more energy. It can store more lithium ions. Okay. So any kind of application, it provides flexibility, right? So that's why high surface area and porosity enhance catalytic and storage applications. They offer multiple transport pathways for ions and electrons. Okay, so because of this multi-transport pathway, because of many needles, see, for example, here every needle-like structure provides electronic pathways. So everything. So this nano rod, something like so nano, right? Something what else we can call nano needles, nano rods, nano flakes, nano spikes, right? So these are all participate. These are all participate in transport. These are all act as a electron transport pathways. Electron transport pathways. Okay. So structural hierarchy allows tunable mechanical and thermal properties. We can tune. We can by changing these shapes and structures, we can change the, we can tune the flexibility, we can change the strength, we can modify the strength, so that we can modify, we can tune mechanical and thermal properties. Okay, so self assembly and templating methods facilitate complex architectures. So we can make different architectures, we can make different nano architecture 3D structures. Their bulk-like form eases handling, processing, and device integration. So, making processing also very easy, preparation also a bit easy when compared to one-dimensional nanostructures. Okay. Examples are nanosponges, aerogels. We can see the images of 3D structures. Here also in this image you can see advantages and disadvantages. Higher electrode electrolyte contact area. So we find major applications of 3D nanomaterials in energy sector, particularly in battery technology. So there we can find a good contact between electrolyte and electrode and electrolyte contact area. Okay, because it provides large surface area and also highly conductive 3D network. See, this 3D network we cannot find in 0D, 1D, in 2D. So this is more advantageous, or we can say that promising or potential nature in three-dimensional nanomaterials. It has highly conductive 3D networks and also rich surface active sites. So all these properties put 3D nanomaterial in a better way, in a better way for many applications like 3D printing applications also, like for mechanical strength, right? Particularly in energy field. Okay, in energy field. So these are the examples, these are the properties of three-dimensional materials. So let's see the real time. So let's see, am I prepared any, if I worked on three-dimensional materials or not. I think I worked in I think I have prepared Bismuth vanadate 3D structures. Let's see. Uh, Bismuth vanadate 3D structures. Uh, let's cancel, remove all these things so that, yes, this is very beautiful, very, very beautiful. Where is it? Yes, excellent. Yeah, this is it's not a nano, it's a microspheres. Just for your understanding, this is a 3D material, but it is a not nano material. It's a microspheres actually. Yes, I think it's a microspheres. Microspheres, or yes, in the range of. Okay, see this the 3D structure. See the porosity. You can see the gaps. You can see the gaps here. You can see the gaps here. So it is a 3D structure. It is a 3D structure. You can see 3D structure. And let's remove all these things. I think here also you can see something like 3D structures, but it's MOS2 nano petals. But because of some aggregation, it looks like a 3D structures. Bismuth vanadate. Let's check. Yes, it's a dendrite structure. Yeah, this is BiBO4, bismuth vanadate, and I have prepared this material to treat air pollutants, organic pollutant removal, and also I have tested this photoelectrochemical performance. This is related to water splitting. Okay, so this is my name, and we have done this work in 2022. See this, it's a beautiful structure. See this one. See, this is nano architectures. Nano architectures. Okay, it is a dendrite structure. It is a dendrite structure. You can see this one. It looks like a combination of 2D and 3D. I will show you in web some of the 3D nanostructures, 3D nanomaterials. See this one. Yeah. So this one we have seen earlier. See, these are all 3D nanomaterials. See, 3D nanomaterials. See some nanocubes. See this one. This is a nanocube. 3D example. 3D nanomaterial example. Nanocubes. Okay. Nanocubes. I think I will show you gold nanocubes. Yes, very beautiful. See this one. Gold nanocubes. Gold nanocubes. And also we have different nano structures for gold. See, these are all gold, gold nanorods, gold nanoparticles, gold nanorods, gold nanocubes, gold nanoflowers, gold nanotriangles. Wow. See, these are all different nanostructures of gold. Okay, different nanostructures of gold. So, many nanostructures. Many nanostructures in this picture, all gold nanostructures, triangles, something like cubes, hexagon, octagon. So these are all examples of nanostructures. Wow. I think, see the nanoparticles, nanospheres, hmm? Small, ultra small nanospheres, right? So these are all examples for 3D nanostructures. Okay, I hope you understood. I will search any of my articles related to 3D. 3D. I think this one also. Yeah. See this one, MOSE2, molybdenum selenium. See the 3D structure. So we have prepared this 3D structure for what application? For energy application. For energy application. Yes, for solar cell application. Okay, for solar cell applications we have prepared this material 3D structure. 3D for in case of 0D I have prepared SnO2 quantum dots, right? For one dimensional I have prepared copper nanowires, CDS nanorods, hmm? And also for two dimensional materials I have prepared graphene, amexine, graphic carbon nitride, right? We have seen all the examples, and also we have seen all the applications of that particular materials, right? In 3D, this MOSE2, MOS2, right? And bismuth vanadate, BiVivo4 dendrite structures, right? We have seen nanocubes, yes. So this one also I have used for water splitting application, right? Water splitting application. Okay, so these are the examples for 3D materials. Now let's go back to our presentation. Okay, so now we have discussed about three, four types of nanomaterials, right? We have discussed about four types of nanomaterials: zero-dimensional materials, one-dimensional materials, and two-dimensional materials. Okay, so now we will compare. Now we will compare all the 3D materials. Okay. Now we will compare all the three materials: zero-dimensional materials, one-dimensional materials, 2D materials, and 3D materials. So in this lecture, we have discussed so far three types of nanostructures, and we have discussed the properties, and also we have discussed the what are the particular properties and also particular advantages. So what which type of materials have application, different applications in different areas. Some applications have more advantages in medical field. Some materials have more advantages in electronics. Some kind of nanomaterials have more advantages in environmental applications, and some applications like 3D materials have advantages in energy field, particularly in batteries. Okay, so likewise, so far we have discussed about the properties and applications, properties and applications in uh, properties and applications of these nanomaterials in different fields. So now we will discuss about the comparison. Okay, comparison of these three nano materials 0D to 3D. Okay, so we will review, or we will overview all the four types of nanomaterials. Okay, now so I want to show you all these things once again. Okay, classification of nanomaterials. I hope you can understand now this 0D materials, 1D, 2D, and 3D. See, previously we have discussed about this picture, right? So 0D, it should all the dimensions must be within nanoscale. In one dimensional, so one dimension must be beyond nanoscale range. In 2D, so two dimensions are beyond nanoscale or within nanoscale also, no problem, but the thickness must be, one dimension must be within nano range. Okay, so 3D, it looks like a bulk, but it should be within, all the dimensions must be within nanoscale, within 100 nanometers range only, otherwise it can be called as microstructure. Okay, so if all the dimensions within 100 nanometers, then we can say that it is a three-dimensional nanomaterial. Okay, 3D nanomaterial. Now here you can see the some images, of nanoparticles, zero-dimensional nanoparticles. These are zero-dimensional nanoparticle, zero-dimensional nanoparticle, right? And then you can see the difference. Even the difference is small. You can see the change in optical properties, right? The change in optical properties. Here you can see the functionalization. Okay, functionalization. Yes, yeah. This is functionalization. So functionalization is can be done biofunctional unit, or we can add some hydrophilic stabilizers. We can add some hydrophobic anchors. So in this way we can functionalize. So functionalization improves stability. Functionalization can improve the reactivity with surroundings, right? So these are 1D materials. Nanorods, nanotubes, nanowires. Best examples, carbon nanotubes, right? So different types of carbon nanotubes. SWCNTs, that means single wall carbon nanotube, double wall carbon nanotube, multi wall carbon nanotube. We have multiple, we have different types of CNTs available for different applications, for different mechanical strengths, right? So these are examples for 1D nanomaterials. 2D nanomaterial. Can you remember what is this? GC3N4, graphitic carbon nitride, right? Graphitic carbon nitride. And then 3D, 3D nanostructures, right? 3D nanostructures. 3D nanostructures provide more porosity. What are the advantages of more porosity? In energy applications, it is very useful to store more energy, and also it provides higher electrical transport pathways, electronic transport pathways. Okay, this is 3D nanostructures advantages and disadvantages. Okay, now we will see the comparative analysis of 3D 0D to 3D nanomaterials. Check this image once. Check this image. So comparative analysis of zero dimension to 3D nanomaterials. Here you can see. Here you can see 0D materials, nanoparticles, fullerenes, quantum dots. These are all examples for zero dimensional material. See the quantum dot, nanoparticles, fullerenes, and then one dimensional materials, nanowires, nanofibers, nanorods, nanotubes, nanohorns, right? Nanohorns. So these are all examples for one dimensional material. Okay, one dimensional materials. Sorry. Then two dimensional materials. So two dimensional material means nanowires, nanorods, right? Core shell nanorods, core shell nanowires. So these are all under core nanorods, nanowires, all comes under uh, one dimensional material. Next, two dimensional materials. Sorry. Nanosheets, nanolayers, nanofilms. What are the best examples for two dimensional materials? Graphene, amexine, GC3 and 4. These are all 2D materials. Next, 3D materials. Okay. Now we will see the comparative analysis. 0D to 3D nanomaterials differ in size confinement, properties and application. So all the four types of nanomaterials are different in dimensionality and also in confinement. Confinement. What is confinement? Here you can see. Here you can see in this image. See the confinement. Confinement in all dimensions, right? It is confinement in two dimensions, confinement in one dimension, right? So this is the confinement. Okay, confinement. So 0D to 3D nanomaterials differ in size confinement, in size confinement, properties and applications. Okay, and applications. 0D shows complete confinement. 0D shows complete all the dimensions. Like in all the three dimensions, it is confined. Confined all the from across all the dimensions, it is confined. 1D confines in two axes. Two axes. For example, if you take x, y, and z, x, y it is confined. Okay, x, y confined. only one dimension. It can go beyond nanoscale. Okay, so 2D confined to 1, 3D has no confinement, 3D has no confinement. Okay, so I will do one thing. I will bring this image so that you can understand better. Now you can understand. See, 0D shows complete confinement. So this 0D confined in all dimensions. In 3 dimensions, so it is confined. Okay. Then 1 dimension confines in 2 axes. 2 axes. So that means, see, this one-dimensional nanorod or nanowire, it is confined in 2 dimension. So it is free in one direction. It is free in one direction. It can go any scale. It can go beyond nanoscale. Okay, in 2D nanostructure confined in one direction. Okay, so only one direction it is confined, only in one direction. Okay, 3D has confined. 3D has no confined. 3D has no confined. It can stretch in any direction up to nanoscale. Up to nanoscale. If it extend beyond nano size, beyond 100 nanometer, then we cannot say it is a nanomaterial. So that's why it has no confine up to nano size, up to nano size. Okay, next, surface to volume ratio generally decreases from 0D to 3D. So surface to volume ratio is higher for zero dimensional material than to 1D, then 2D, then 3D usually. Okay, quantum effects are most pronounced in 0D and diminish in higher dimension. Okay, quantum effects are most pronounced in 0D. That's why if you think about quantum dot LED, so that is it is more advantageous because it provides high surface area, right? High surface area, and also because of this confinement, it can provide better colors. If you see this image, you see this image, yeah, these are all quantum dots. So quantum dots can give you bright colors, because of quantum confinement, because of quantum confinement. It is confined in all the directions. It is confined in all the directions. That's why it is confined in 3 dimensions. That's why it shows better quantum confinement effect. Okay, mechanical flexibility increases from 0D to 2D, but decreases in rigid 3D structures. So if it is rigid 3D structures, if you bend, it will broke the structure. Okay, it will broke the structure. That's why, so flexibility increase up to 2D, 0D, 1D, 2D. 2D is more flexible, 1D is flexible, 0D is not that much. Okay, so flexibility, mechanical flexibility increases 0, 1, 2, up to 2D. Up to 2D flexibility increases. Okay, but 3D structures not that much flexible. Okay, so that's not the purpose. Okay, we can find other purpose, other applications for 3D structures. Okay, so application suitability varies. Yeah, this is very informative. So zero dimensional for bio, 1D for electronics, 2D for sensors, 3D for energy, right? So that's what I am telling you from the starting onwards, that we can find different applications. We can find different applications for different dimensionality nanomaterials. For different dimensionality nanomaterials. Okay. So 0D for bio, 1D for electronics purposes, for 2D for sensing, and 3D for energy. It's not a restricted applications. We can find more applications just for understanding purpose. So I have written one one application. Okay, the choice depends on the interaction mechanism, stability, and process requirements. Okay, so because the preparation is different, the preparation process is different, and also while using for application, so we will use different approaches and processes and methods, right? So depends on that, the final output will decide, the final output will be measured. Okay, so that's why, so this is the comparative analysis. So one thing you need to understand very clearly is the confinement 0D, 3 ways confinement, 1D, two confinements in 2 ways, right? 2 axis confinement. In 2D, only one confinement, one direction confinement. 3D, no confinement, right? That's it. I hope you can. Yeah. Then we'll discuss about surface to volume ratio across dimensions. Okay, surface to volume ratio across dimensions. So the surface to volume ratio is highest in 0D and decreases progressively through 1D, 2D, and 3D. That's what we have discussed here, right? So here, surface to volume ratio generally decreased from 0D to 3 dimension. Okay, so the surface to volume ratio is highest for 0 dimensional materials like nanoparticles, quantum dots, like that, and decreases progressively through 1D, 2D, and finally 3D. Okay, high surface to volume ratio in nanomaterials enhances reactivity, adsorption, and catalytic behavior. We have seen this, right? So earlier, so in higher surface to volume ratio plays a major role, right? We are discussing this point from starting onwards. Okay, so it provides enhanced reactivity. So based on this point and this point, so which materials provide better enhancement? Obviously 0D materials, right? So 0D quantum dots demonstrate exceptional optical adsorption due to extreme surface to volume ratio. So in this figure also you can see surface to volume ratio in nanomaterials, highest surface to volume ratio, exceptional optical adsorption. So that's why, so for most of the optoelectronics and for optical properties, so 0D nanomaterials are preferred choice. Okay, preferred choice. 1D nanofibers benefit from high surface to volume ratio in sensing and charge transport applications. Charge transport application. Why? Because one-dimensional nanomaterials provides unidirectional property, right? Unidirectional property. So that electron transport is much easier. Okay, much easier. That's why. So charge transport application purpose we will use 1D nanowires. See, that means it doesn't mean that 3D and 2D doesn't provide charge transport applications. No, that's not right. Okay, 2D sheets expose nearly all atoms at the surface, enabling efficient surface functionalization. Okay, so two-dimensional materials provides surface area. That means all the atoms will come onto the surface, so that all the atoms available in reaction. Okay, 2D sheets. Yeah, 3D structures retain moderate surface to volume but gain volume dependent properties such as mechanical strength. Okay, such as mechanical strength. So 3D structures provide higher mechanical strength because of that bulk structure property. Okay, because of that bulk structure property. Okay, surface to volume is a critical factor in designing nanomaterials for catalysis, drug delivery, and supercapacitors. Okay, so from this slide, what we have learned, surface to volume ratio is high for zero dimensional material. Mechanical strength is high for 3D materials. Which nanomaterials provide better charge transport, one dimensional material. So in which nanostructures all the atoms on the surface, 2D materials, right? Now let's see this picture. Quantum confinement effects. I think we already discussed these points. 0D, three-dimensional confinement. This is one-dimensional nanowires, 1D materials. Confinement is in two ways. See here, this way, this way, this way. X on X, Y axis, Z axis. All the across all three axes we have confinement. But here you can see the confinement in two directions. Okay, so here Z axis confinement, Y axis confinement, but there is no confinement along X axis. So that's why it can elongate, it can extend, it can extend in X axis. It can extend in X axis. So similarly, so this is a two-dimensional nanomaterial. Okay, two-dimensional nanomaterial. So in two-dimensional nanomaterial, confinement is only in one direction. Here, for example, here you see z-axis. So confinement is along z-axis, and it can elongate along x-axis, and also in this direction. In this direction, y direction, it can extend x-axis, along x-axis, it can extend. Okay, so this is very uh, interesting picture to illustrate the confinement, so that you can understand very um, clearly, right? Each confinement direction converts a continuous k in a discrete quantum number n. Okay, so this is n represents confinement. Okay, k represents elongation, converts. Right, we will see some points. Quantum confinement occurs when particle dimensions approach the exciton Bohr radius. We already seen in previous class. Bohr exciton Bohr radius means when it approaches exciton. So that means the average distance between electron and hole pair. The average distance between electron and hole pair in any exciton. Okay. So in 0D structures, electrons and holes are confined in all three dimensions, leading to discrete energy levels. So in 0D structures, in 0D structures, so electrons and holes are confined. Electrons and holes are confined in all the three dimensions. Okay. So in 1D and 2D materials show partial confinement. Partial confinement affecting their band structures and optical properties. Okay, and optical properties. Reduced dimensions increase band gap energy. Reduced dimensions, that means decrease in the particle size. So what happened when particle size decreases? Obviously band gap will increase, right? That's what it here. So reduced dimensions increase band gap energy, enabling size tunable photoluminescence. So by changing the band gap, we can change the optical properties, luminescent properties, right? So that's what it is, photoluminescence. Quantum confinement significantly enhances the sensitivity and selectivity of sensors, okay, of sensors. It allows precise control over electrical and optical behaviors in optoelectronic applications. Nanomaterials with confinement are ideal for LEDs, solar cells, and bioimaging agents. So we can find all the applications by nanomaterials. Okay, nanomaterials with confinement are ideal for LEDs, solar cells, and bioimaging agents. Study this image. This image is belongs to, see, on x-axis we have diameter of nanoparticle. On y-axis we have surface energy. Surface energy. So what is the relation? Particle size, surface energy. Surface energy, surface energy can be understood from surface area point of view, right? Surface area point of view. Then surface area can be understood from size of the particle. Okay, size of the particle. So here you can see in this image, so from right to left, the size, the diameter of particle is decreasing, and from left to right, see here, the surface energy is increasing. Surface energy is increasing. So from this, you can understand. So for for ultra small nanoparticles, surface energy is high. Surface energy is high. Okay. Surface atoms in nanomaterials possess unsatisfied coordination, increasing surface energy. Okay, so surface atoms, surface atoms in nanomaterials will provide surface energy. Higher surface energy enhances chemical reactivity, making nanomaterials ideal catalysts. So that's what. See, for catalysis application, we need high surface energy. We need high surface energy because it has to immediately react with the surroundings. Okay, so for catalysis applications, we need high surface energy. Okay, yeah. So in 0D particles, surface energy drives aggregation unless stabilized by surfactants or ligands. Okay, 0D materials, so surface energy comes from surface energy was influenced by aggregation and also functionalization. Okay, in 1D and 2D materials, it show facet dependent surface energies affecting reactivity and stability. So in 1D and 2D, you can see here the phases. The phases. This is one phase, another phase, another phase. This is another phase, like that. So these facets plays a major role in surface area and also this surface energy. Okay, affecting reactivity and stability. Okay. So surface energy is tunable via doping, coating, or functional group modification Okay, and also high surface energy contributes to better absorption and charge storage capacity. High surface energy contributes to better absorption and charge storage capacity. So if high surface energy uh, contributes to charge storage. So this charge storage is the major factor in energy storage devices. Super supercapacitors, batteries, right? So I think, yeah. So control over surface properties is essential in applications like catalysis, sensing, nano medicine. Okay. So synergistic properties across dimensionalities. See, even though individual dimensionality nanomaterial provides better applications and advantages, but still if we mix, if we make a composite with different dimensionality materials, we have advantages. For example, I have shown you here, in my research previously, I have prepared uh, core shell nanostructure, right? So core is nano rod, that is 1D material. Quantum dot is 0D material. So I have made 0D, 1D nano composite. Okay, 1D and 0D. So it has some advantages. Likewise, 1D and 2D advantages. Likewise, 3D and 0D. For example, if you make a 3D flower, 3D nano flower, so you can decorate 0D nanoparticles over the 3D nano flower, right? So it's a good combination, so that you can increase surface area, you can increase surface energy, so that many advantages. So that type of information here we can see. See, 0D, 2D hybrids. So this combination will enhance charge separation in photocatalysis due to interfacial interactions, right? So this combination provides interfacial interactions. Okay. So next, 1D, 2D, 1D, 3D combinations. Okay, 1D, 3D combinations. So this combination improves mechanical reinforcement and electrical conductivity in composites. See, if you are mixing two different dimensionality materials, we can call it as a nano composite. Okay, nano composite. Okay, so 1D 3D combination improves electrical conductivity. Then heterostructures. Heterostructures exploit both quantum confinement and extended network properties. Network properties. See, I have shown you something like okay, right. So I already shown you, right, previously. So 0D, 1D, 2D, 2D, 0D. You can decorate quantum dots over 2D surfaces. For example, C3 and 4, right? So it is a 2D layered structure, and also MOS2, 2D layered structure. So over MOS2, 2D layered structure, you can decorate with nanoparticles. You can decorate with gold nanoparticles. You can decorate with SNO2 quantum dots, right? So that is 0D, 2D, right? So likewise 1D, 2D. So these heterostructures can provide extended network properties, and also hybrid nanomaterials. This hybrid nanomaterials means, so mixing 1D, 2D, 3D, 0D, 2D, 3D. So likewise different combinations. Okay. So these different combinations improve performance in batteries, supercapacitors, and multifunctional applications. Okay, multifunctional applications. So interdimensional hybrids provides greater design flexibility. So by selecting these different combinations, you will have you can improve your efficiency. You can improve your efficiency. For example, if you want more strength, more mechanical strength, so you can integrate the quantum dots or some nanoparticles with the 3D structures, right? With 3D structures, so that the mechanical flexibility will increase, mechanical strength will increase. Okay, mechanical strength will increase. So these are all the advantages. Synergistic design. You can design different designs. Okay, you